Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to your YouTube channel Chandan Physics. In this video, we are going to discuss particle in a squirrel potential for that of bound state. Let's begin. We consider a particle of mass m and total energy E confined in a potential well, and that potential well is defined as that potential will be 0 in that of region 1. Let me treat it as x is at minus a and x is at plus a, that is the potential axis. In region 1 and region 3 the potential will be 0, and in that of region 2 it will be u naught minus u naught. This is the squirrel potential, and the potentials of that of various regions are given like this. Let me treat the wave function represent that of region 1, let psi 1, and the wave function again represent that of region 2, let psi 2. For that of region 3 it will be psi 3. Then we use time independent Schrodinger equations in these three regions, and then we get its solution, and after solving these solutions we should find the eigenvalues and eigenfunctions of that particle in squirrel potential for that of bound state. So in region 1 we use time independent Schrodinger equation, that is d square psi 1 by dx square minus 2me divided by h cross square psi 1 is equal to 0. This treat as a constant, let alpha square, and our solution psi 1 is equal to a e to the power alpha x plus b e to the power minus alpha x. In region 2, similarly in region 2 the time independent Schrodinger equation is applied, so that will be d square psi 2 by dx square plus 2m by h cross square e plus e u naught of psi 2 is equal to 0. So that term is treated as a constant beta square. So the solution will be psi 2 is equal to c cos beta x plus d sin beta x. And here in region 3 the wave function is psi 3, so the time independent Schrodinger equation is applied here, that is d square psi 3 by dx square plus 2m by h cross square e minus 0. Since the potential in that of region is 0, psi 3 is equal to 0, we treat it as a constant, therefore alpha square is equal to 2m by e by divided by h cross square. So the solution psi 3 is equal to f e to the power alpha x plus g e to the power minus alpha x. Look at these two conditions or these three solutions. For a well behaved wave function, let psi x tends to 0 for what? For x plus minus infinity. Since b e to the power minus alpha x tends to infinity, so for x tends to minus infinity, again f e to the power plus alpha x tends to infinity, so for x tends to plus infinity, so f is equal to 0 here. So the solutions are changed to, the solutions are written like this: psi 1 is equal to a e to the power alpha x, there will be no contribution of that term. Again psi 2 as function of x is equal to c cos beta x plus d sin beta x. Then the wave function 3, that is g e to the power minus alpha x. These three solutions are represented as the squirrel potential for these three regions accordingly. 1, 2 and 3, that is for region 1, that is for region 2, that is for region 3. Let us find out these amplitude terms. So A, C, D and G, these amplitude terms are derived. We have to implement the boundary conditions of that of squirrel potential. Let us introduce the boundary conditions. So the boundary conditions, boundary condition 1, psi 1 of x is equal to psi 2 of x at that of x is equal to minus a, and again its differentiation also same. Again another boundary condition, psi 2 is equal to same as that of psi 3 at x equal to a, and its differentiation at that of same limit will be same. These four boundary conditions express four different types of equations. So when we implement first boundary conditions for that of wave equation psi 1, psi 2 and psi 3, we get first equation. Again use the second boundary condition, we get the second equation, and use the third boundary condition, we get the third equation, and use that of fourth boundary condition, we get that of fourth equations. These boundary conditions are used here, psi 1, psi 2, psi 3, use that equations. Accordingly we derive the respective equations. Equation 4 number of equations are derived as far as the boundary conditions are concerned. Let us mathematically treat these four equations to derive the coefficients like A, C, D and G. First, adding equation 1 and 3. Equation 1 and equation 3, when we add these two equations, we get 2c cos beta a is equal to a plus c e to the power minus alpha a. Again adding equation 2 and equation 4. Adding equation 2 and equation 4, we get 2c beta sin beta a is equal to alpha of g plus a e to the power minus alpha a. Now dividing this 2, that means dividing v by vi, so we have alpha is equal to beta tan beta a. Alpha is equal to beta tan beta a. Subtracting iv from ii, subtracting that 4 number equation to that of second number equation, we get 2 d beta cos beta a is equal to alpha of a minus c e to the power minus alpha a, and again subtracting that equation 1 from equation 3. Equation 1 is subtracted from that of equation 3, we get another equation, that is 2d sin beta a is equal to g minus a of e to the power minus alpha a. Now using equation v double I to that of v triple I, means the alpha value is substituted here. So what we have? We have 2 d beta cos beta a is equal to, in place of alpha we substitute beta tan beta a, that is beta tan beta a of a minus c e to the power minus alpha a. Again multiplying a factor, that is beta cos beta a, in that of equation. So we get 2d beta cos beta a into sin beta a is equal to, again multiplying that factor on that of both sides, we have beta of g minus a cos beta a into e to the power minus alpha a. Look at these two equations, equation x and xi. That value is tan beta a, means that is sin beta a divided by cos beta a. When we multiplied a sin beta a on both sides, that will be 2 d beta cos beta a into sin beta a, and inside that RHS we have sin square beta a. Look at these two equations, the LHS of these two equations will be same when we extend it tan beta a as sin beta a by cos beta a. So equating equation number x and xi, what we have? Beta of a minus j sin square beta a divided by cos beta a e to the power minus alpha a. This portion will be same as that portion. That portion will be beta of g minus a cos beta a into e to the power minus alpha a. So a minus g sin square beta a is equal to minus of a minus g cos square beta a. A minus g, that is sin square beta a plus cos square beta a, is equal to 0. Sin square beta a cos square beta a is equal to 1. So a is equal to g. And again when we implement from ix and x equation, we have d is equal to 0. A is equal to g and d is equal to 0 are derived from these equations. So using these values, a is equal to g and d is equal to 0, we get a is equal to c cos beta a into e to the power alpha a. This is known as the first group of solution. This is known as the first group of solution. Let us derive the second group of solution. How that second group of solution is derived? Similarly, dividing equation number v triple I and ix, equation number v triple I and ix, when we dividing these two equations, where we consider a not equal to g and d not equal to 0, alpha is equal to minus beta cot beta a. Alpha is equal to minus beta cot beta a. Therefore we use the value of alpha in that of equation v double I. When we substitute the value of alpha in case of v double I, not v double I, in case of v triple I, just to implement the value of alpha here in v I, what we have in v I, look v I, just in place of alpha we substitute the value of alpha here. So 2 c beta sin beta a is equal to minus beta cot beta a of g plus a e to the power minus alpha a. Now multiplying cos beta a on both sides, there will be no such change. Now multiplying beta sin beta a in equation v double I, in equation v double I, multiplying beta sin beta a, not v double I, that is in equation v, in equation number v, here is the equation number v, we multiplying what factor? Beta sin beta a. So 2 c beta sin beta a cos beta a is equal to just beta sin beta a multiplied here. Look at these two equations. These sides, that sides are same, therefore the RHS will be definitely same. Now equating these two equations, we get beta of a plus c sin beta into e to the power minus alpha is equal to minus beta of a plus c cos square beta a divided by sin beta a e to the power minus alpha a. So a plus c of sin square beta a plus cos square beta a is equal to 0, sin square beta a plus cos square beta a is equal to 1. Therefore a is equal to minus c and c is equal to 0. Therefore g is equal to d into sin beta a into e to the power minus alpha a. That is the second group of solution. That is the second group of solution. Previously we derived the first group of solution. First group of solution, equating these equations, we get the first group of solution. Here proceeding the same method and equating these equations, we get the second group of solution. Now we write combiningly what we have derived as first group of solution and second group of solution. From first group of solution, a is equal to g and d is equal to 0. Therefore, a is equal to c into e to the power alpha a cos beta a. That is the first group of solution. First group of solution. Here in second group of solution we derived a is equal to minus c and c is equal to 0. That means g is equal to d of e to the power alpha a sin beta a. That is the second group of solution. Second group of solution. By using first group of solution and second group of solution, we can easily define what should be the eigenvalues and eigenfunctions in case of that particle in that of square well potential for bound state. Let's look at that. Energy, eigenvalues and eigenfunction. Here alpha square is equal to minus 2m divided by h cross square as we define in that of time independent Schrodinger equation for that of regions like region 1 and region 2 and region 3, and beta square 2m of e plus u naught divided by h cross square. So alpha square plus beta square is equal to 2m u naught divided by h cross square. Now multiplying a square on both sides, we get u naught by delta, that is delta is equal to h cross square divided by 2m a square, that will be h cross by a square divided by 2m, that is the energy of particle, total energy of particle in that of well. What indicates that equation? Here the uncertainty in position in that of hole having the width a of potential well, then the uncertainty in momentum be h cross by a, and the minimum energy of that of particle of the well is delta is equal to h cross by a square divided by 2m, that is the minimum energy of that of particle that in that of well. So let's introduce that of first group of solution. Tan beta a is equal to alpha by beta. Look at here, alpha is equal to beta tan beta a. So tan beta a is equal to alpha by beta. Here tan beta a is equal to alpha by beta is positive, since alpha and beta both are positive, therefore alpha by beta is positive. Then the range of that beta a in between pi to 2n plus 1 pi by 2, where n stands for 0, 1, 2, 3 like this. Now the term u naught by delta is equal to alpha square plus beta square of a square, alpha square beta square plus a square. Now we substitute in place of alpha square. Look here, tan beta a is equal to alpha by beta, so alpha is equal to beta times of tan beta a, so alpha square is equal to beta square tan square beta a. So in place of alpha square we substitute beta square tan square beta a plus beta square a square. In these two terms beta square taking as common, so beta square tan square beta a plus 1 of a square, tan square beta a plus 1, that will be sec square beta a. Sec square beta a to that side 1 by sec square beta a, it will be cos square beta a, sorry cos beta a. Cos beta a is written like this, and magnitude of cos beta a will be beta a times of delta by u naught square root, that is the cos beta a, magnitude of cos beta a. Again using that of second group of solution, in case of second group of solution we taking as look here, in that of second group of solution we introduce alpha is equal to minus beta cot beta a. Here second group of solution, the beta a range in between 2n minus 1 pi by 2 to n pi, where n stands for 1, 2, 3 like this. So u naught by delta is equal to alpha square beta square of a square. So in place of alpha square we substitute beta square cot square beta a plus beta square a square. So beta square taking as common, that is cot square beta a plus 1. So cot square beta a plus 1 is equal to, that is cos square beta a. Cos square, that means 1 by sin square beta a. So sin beta a magnitude is equal to beta a under root of u naught by delta, the magnitude of sin beta a. So look at here, from the above analysis we conclude that if we draw a graph in between cos beta a and sin beta a taking as that of graph, and beta a times of delta by u naught. Let us draw a graph. What we have here, when we draw a graph, zero, here we taking as pi by 2, pi, 3 pi by 2, 2 pi, and 5 pi by 2. So cos beta a and sin beta a are treating like this. This is the cos beta graph first. The cos beta graph. Then the sin beta graph. This is the sin beta graph, the dotted line. At the intersection in between sin beta a and cos beta a, this is the graph range, that is delta by u naught under root of beta a in that of axis. So the lines this one is the line, this one is the line, this one is the line. In between the intersection of cos beta and sin beta a, these lines are u naught by delta as 1, here u naught by delta 4, here u naught by delta is equal to 70. These are the graphical representation of these two group of solution. Let us, according to our findings, the findings of first group of solution and second group of solution, the solutions of these wave functions are psi 1, psi 2, psi 3 and its groups are basically find out. So when we plot the graph, for that of energy levels, n is equal to 0, n is equal to 1, 2, 3, this is as u naught. So what happened? This is for psi naught of x, and when n is equal to 1, this is psi 1, and when n is equal to 2, it is psi 2, when n is equal to 3, the graphs are like this, it is psi 3. These are the graphical representation of these wave functions. What are the conclusions that drawn from this squirrel potential of that of particle for that of bound state? So the conclusions we have drawn: Conclusion number 1, when sin of minus x is equal to sin of plus x, the wave function are symmetric. Symmetric, sin of minus x is equal to sin of plus x, and sin of minus x is equal to minus of sin of x, that means the wave function as antisymmetric. Symmetry condition, this will be for antisymmetry condition. Conclusion number 2, the sin of x have even and odd parity alternatively, because u of x, that is the potential, is symmetric with respect to origin. Looking here, the potential that is symmetric with respect to the origin. Third conclusion, due to the factor e to the power minus alpha x, the wave function decreases exponentially. The wave function decreases exponentially. Why? Due to that factor e to the power minus alpha x. Again, due to alpha square, that is magnitude of alpha square, that is probability density, or finding that a particular particle in that of region is directly proportional to e to the power minus alpha magnitude of x. We concluded that the particle is bound to the potential well and unable to go to infinity, like large distances, infinitely large distances. Hence, all the eigenstates when E is less than 0, the energy or that of energy of the particle when less than 0 are bound states with that of potential well. These are the 4 conclusions drawn from these mathematical treatments for that of bound state in case of particle in a squirrel potential. So, what we have discussed throughout that video lecture, here we discussed about particle in squirrel potential for that of bound state. Potentials are given for that of regions. Use time independent Schrodinger equations to derive the solutions, and the solutions are written like this for 3 regions. And to get the amplitude factors, we use the boundary conditions, and as far as the boundary conditions are concerned, the corresponding boundary condition indicates a new equation, and after mathematical treatment of these equations, we get first group of solution, and again similar pattern taken in consideration, and we get the second group of solution, and to use first group of solution and second group of solution, we get the energy eigenvalues and eigenfunctions for first group of solution and the second group of solutions, and a graphical view of that. This is the wave function representation, and what are the conclusions drawn from this type of phenomenon. So, with this useful and informative notes, let me wind up this session. Thank you.